In this section, we're going to switch gears from right triangle trig and now talk about the unit circle. So before we do that, I kind of want to motivate this discussion. We'll talk a little bit about where the unit circle comes from, and then we'll actually solve some problems involving the unit circle. So to start with, let's just think about a triangle. And so I have some sort of triangle here with an angle theta. And theta can really be any angle up until we hit, right? So I could have a triangle here. I could keep creating triangles, but eventually I would not be able to create any more triangles. And that would happen basically after I got to 90 degrees. So notice if I do get to 90 degrees, and keep in mind this is also a 90-degree angle, but I can no longer have a triangle because these two lines here are parallel, and so I've actually created a square or some other shape. But you cannot have a triangle with two 90-degree angles. So the question came up historically. They said, well, what about trig functions? So for example, sine of some angle theta that's greater, really, or equal to 90 degrees. So this could be sine, cosine, or tangent, really any of them. But the question was asked, what happens when the angle gets to be greater than 90 degrees? So what someone came up with is they said, well, let's think about the coordinate plane, and let's put a triangle into the coordinate plane. And so let's say this was a triangle with a 45-degree angle. They noticed, they said, well, actually, so we have this opposite side and this adjacent side. And so sine of 45 degrees is just this opposite. But if we're thinking about this as a coordinate plane, that opposite side is actually y, and the adjacent side is x. And they said, okay, so sine has something to do with the y value. And what y value is that? Well, if you actually figure out what point this is in the coordinate plane, this will have an x coordinate and it will have a y coordinate. And so all you have to do is rotate an angle 45 degrees in the coordinate plane and see what point is on the graph at that spot. Now they also said, well, what about the hypotenuse? And it was decided, well, all of these triangles are similar, sine of 45 degrees. It shouldn't matter what the hypotenuse is because the ratio should stay the same. So they said, really, we need any point on this line. So I could pick any of these points that I want. So let's just pick the point that has a radius or distance from the origin. I'm already getting ahead of myself. But let's call this distance 1. From here to here is 1. And so that way they said, well, in this case, now we don't really have to worry about anything. We can just straight up say that sine of 45 degrees is going to give me y over 1, right? Opposite over hypotenuse. But since the hypotenuse equals 1 and the opposite side is y, we really just get y over 1, which is just y. Same with cosine of 45. They said, well, that's just going to be x. And then the rest kind of follow from there. So we can actually go ahead and define these now. And this will get to my original question was what happens if the angle is greater than 90 degrees. We will get there in a moment. But first of all, let's just define, if I have any angle in the coordinate plane, and we would say that the point xy is on its terminal side. Then sine of theta is y, cosine of theta is x, tangent of theta. So this would be opposite over adjacent, which is y over x. And then we just have to take the reciprocals for the reciprocal functions. So we have cosecant is 1 over y, secant is 1 over x, and then cotangent of theta is x over y. And so just like with the triangles, we're now going to be using these relationships but it comes directly from that idea of the triangles. Now here's why this is useful. Let's say that now my angle was something that is greater than 90 degrees, right? So 90 degrees would put me right on the axis, the y-axis. But if I was at some angle greater than 90 degrees, now the question is, well, what do we do? And so what happens here, there's something that's really kind of incredible. If you put a triangle right here, and you find the coordinates of this point, let's call this x and y, these relationships still hold true. Even though this angle is actually greater than 90 degrees, sine of this angle theta is still equal to whatever coordinate this is right here. And the reason is because if I actually put this triangle here, let's call this some angle, I don't know, let's just call it phi for the sake of phi, then it actually works out that sine of theta is going to be equal to sine of phi. Same with cosine of theta, and same with tangent. All of these will be equal, except for one minor change. You might end up with a plus or a minus. So notice how x is actually negative over here, and y is actually positive. So just keep that in mind, that you will potentially end up with negatives and positives, but for the most part it works out. So this is a pretty remarkable result. Okay, so that's just kind of a discussion to sort of build up the topic of the unit circle. Let's actually talk about what the unit circle is. And if you look in Canvas, you'll actually see a completed version of this, but I'll go ahead and show you how we get all these points, how we get all those on that completed circle. So the first thing I'm going to do is I'm going to create a circle, and I'm going to say that the radius of this circle equals 1. So that means that if I were to draw a line from the origin out to the edge, this distance is 1. And we're going to pick all of our special right triangles that we saw in the last one, and we're actually going to put them onto this unit circle. Now I put 30 degrees here, but I actually want to do this all in radians. Just know that it can also work for degrees. Okay, so here's our first triangle, pi over 6. Now if you're checking back into our notes, you'll notice that our special right triangle with pi over 6, the opposite side was 1, the hypotenuse was 2, the adjacent was the square root of 3. But I actually need to scale this because I want the hypotenuse to equal 1. So I'm going to divide everything by 2. Divide that by 2. And I end up with a similar right triangle. So similarity just means that the triangle was scaled to be bigger or smaller, but the angles all stay the same. And so that tells me that the opposite side is 1/2, the adjacent side is root 3 over 2. And that actually gives me the coordinates of this first point on the unit circle. Square root of 3 over 2, comma 1/2. And we can do that with all the rest of the angles. So if we go up to pi over 4, you end up with root 2 over 2. And then for pi over 6, which I know this is becoming a mess, you end up with 1/2 and then root 3 over 2. Additionally, there's a couple of extra points. So if I don't rotate at all, this would be an angle of 0 degrees or 0 radians. This is the point 1, 0. And then up here, if I rotate pi, this is the point 0, 1. So x is 0 and y is 1. And then this pattern is actually going to repeat. So if you come over here to the other side, going around the circle here, we end up with, so the first one here, I have to add pi over 6 to pi because I'm going to go just that much further, again using all the special right triangles. So if you do this, you end up with 7 pi over 6. and then we're going to go pi over 4. So I'm really doing all the exact same triangles. These are still the special right triangles. Oh, shoot. I just noticed I made a mistake. This should actually be pi over 2. So I'm actually adding, I knew something looked wrong. Pi over 2 plus pi over 6. So this angle is actually 4 pi over 6, which we would reduce to just 2 pi over 3. Apologies for the mistake there. So this angle is actually 2 pi over 3. And then pi over 2 plus pi over 4 would actually give me 3 pi over 4. So the next angle is 3 pi over 4. And then finally we end up right here, and this is going to be 5 pi over 6. And now all of these points will actually repeat themselves because they're sort of the mirror images on the other side, except now we're going to have all the x values will be negative. And then this one here will be like that. And this continues around the circle. Like I said, you can actually look in Canvas and get a copy of this, which we'll be using throughout this unit. But what you need to know is if I say something like, what is cosine of 5 pi over 6? All you have to do is take a look at this angle of 5 pi over 6. So that would be a rotation of this amount. In degrees, this is 150 degrees, if that helps make a little bit more sense. Looking on your unit circle, you would say, oh, the point, come up here, negative root 3 over 2 and 1/2 is the point on the unit circle. We take a look back. Notice that cosine is equal to x. So then you say, well, that just means that that's the correct answer. So you'd say cosine of 5 pi over 6 equals negative root 3 over 2. And that would be our final answer. So that's really all that we're doing with the unit circle is we're taking these numbers and saying, okay, I got it. I just look on the unit circle, find the correct answer, and then I'm done with the problem. Okay. Now that's all fine. We've done cosine, sine. We haven't really talked about the other ones though. So let's go ahead now and let's do kind of a complete problem here. Let's just say find all 6 trig functions, sometimes I'll use the word ratio, of the angle theta equals, and let's do 7 pi over 6. Okay, so step 1 is you might even want to pause this video and take a look at your unit circle, but step 1 is to take a look at the unit circle. So you go in your unit circle until you find 7 pi over 6. And so hopefully you notice that 7 pi over 6 is the angle over here. And so then you find these coordinates. So the xy coordinates are negative square root of 3 over 2 and then negative 1 over 2. You'll start to develop a pattern here. So notice all the over 6's have the root 3 over 2 first. But don't worry too much about memorizing right now, memorizing the unit circle. You will probably have to do it next year in calculus though. Okay, so we have our x and our y. Now I'm trying to find all 6 trig functions. So all I have to do at this point is say, okay, what's sine of theta? Remember theta was 7 pi over 6. So sine was the y value, so I get negative 1/2. And then I say, well, what's cosine of theta? You will notice that sometimes I leave off the parentheses. Technically, you don't need the parentheses there, but I like to include them just to avoid confusion later on. So cosine is negative root 3 over 2. Okay, we say what's tangent of theta. Now tangent will require a little bit of extra work because it's y over x. Now you do have to multiply the numerator by the reciprocal of the denominator. So there's the numerator, there's the reciprocal of the denominator. The 2's divide out to 1, so, and then also the negatives become positive, so I'm left with 1 over the square root of 3. Now a good practice, I wouldn't mark you wrong at this point, but a good practice is to always rationalize the denominator. So you can multiply the top and the bottom by the square root of 3, and you actually end up with the square root of 3 over just a regular 3 because those two square roots sort of cancel out and I get 3 squared. But I do want to point out that the actual answer is this, right? But it just doesn't look nearly as good as this. So this is what you're going to be expected to do on Delta Math. So please make sure you can get to that point. Okay, so we got sine, cosine, tangent. Let's do the reciprocals. I always like to start with cosecant because it just follows from sine. Now technically cosecant is 1 over y, but really all this amounts to is taking sine and finding the reciprocal of it. That's why it's called the reciprocal function. So notice that sine was negative 1 over 2. I'm just going to flip these, and that'll be my final answer. So it's going to be negative 2 over 1, which is really just negative 2. Maybe I should start boxing all of these, actually. For secant of theta, we get the reciprocal of cosine, so it's negative 2 over the square root of 3. Once again, I would like you to rationalize the denominator. So we end up with 2 times the square root of 3 over just a regular 3. And then for cotangent of theta, I'm just going to flip tangent. So tangent was positive 3 over the square root of 3. Well, this actually simplifies because 3 divided by the square root of 3 is really just the square root of 3 over 1. Couple ways you can think about this. First of all, notice that up here, if I took the reciprocal of that, it would just be the square root of 3 over 1. You could rationalize the denominator again. So you end up with 3 rad 3 over a regular one, so you could cancel those out. But either way, you do end up with a regular square root of 3. And that would be my final answer. Okay. So that's sort of a complete problem. If you were ever asked to find the 6 trig functions of an angle, or really any of them, I could have said find cosecant of theta. This is how you would go about doing it. You find the coordinates, the xy coordinates, and then you can just sort of plug those in. Okay. Now, as a last quick example here, I want to mention one last detail. Where the functions are positive and negative. So in quadrant 1, all are positive. All of the trig functions are positive in quadrant 1. In quadrant 2, only sine and its reciprocal are positive. The others are negative in quadrant 2. In quadrant 3, only tangent and cotangent are going to be positive. And then finally, in quadrant 4, only cosine and its reciprocal, secant, are positive. And you could show this based on where x and y are positive. So if you ever forget this chart, just remember that when y is positive, that means that sine and cosecant will be positive. For tangent and cotangent, both x and y are negative in quadrant 3, which makes the actual value of tangent positive. And then x is positive in quadrant 4, so cosine and secant are positive in quadrant 4. So this helps you identify where an angle is. If I said If I said something like cosine of theta is less than 0 and cosecant of theta is greater than 0, you would take a look at the chart and you'd say, okay, they're all positive here, and cosecant is positive in quadrant 2. Since cosine of theta is negative, this must mean that theta is in quadrant 2. So x is negative and y is positive. All right, and that concludes our sort of intro. I know there was a lot of content in this video, but we had a lot to cover. Most of it was probably introductory / review content, but hopefully that kind of cleared some stuff up.